Masters of None welcome you to this presentation. Here you find out about our question generation and answering system. We begin with question generation. We start by pre-processing the article, dividing it into paragraphs. Then we generate candidate sentences from which we want to generate questions. These candidate questions are then passed through a post-processing system. We then score these questions in our evaluation system, and this whole pipeline gives us beautiful looking, grammatically correct questions. After article pre-processing, we select candidate sentences to generate questions from. The idea here is that good questions should just not be grammatically correct and answerable from the passage, they should also ask important questions. And to do that, we have a modified TF-IDF scoring scheme, which we use to find the most important sentences from the article, from which we then generate questions.
We then generate questions from each sentence in a four-step process. We build a customized dependency parse tree, split apart long sentences, generate holes in the tree, and finally construct the question. The modified dependency parse tree is a mutable wrapper of Spacy's dependency tree that serves as an integral and novel aspect of this project. It tracks implicit references to subjects and objects through a propagation algorithm, where the subject may come, for example, from the parent of a coordinating conjunction. The tree may be partitioned and can convert passive phrases into the active voice. The propagation recursively spans the whole tree and employs a rule set that determines whether subjects and objects propagate down or up through conjunctions, complements, and clauses. We use the partition feature of the tree to split sentences that are too long along conjunctions and clauses while still maintaining those implicit references. We then select a specific node of the tree to be the answer of our question and delete both it and its children, creating a hole. We select holes to be subjects, objects, prepositions, and their modifiers, but also causes and explanations. We repeat this process on the active form of a passive sentence if available. To build our question, we then flatten the tree, include those implicit references, and follow a set of rules for choosing the who, what, why, the auxiliary, and verb tense. The interrogative is chosen based on the whole's part of speech tag and name entity tags, but also on the token's semantic similarity to words about people, places, and times. We also shift prepositions to add complexity.
Once we have the questions, we do post-processing, where we also do co-reference resolution. After that, we pass these candidate questions into our evaluation system, which scores and ranks all these questions. Apart from having modified TF-IDF scoring and question length as criteria, the main component of the evaluation system is the trigram language model, trained on the entire training data given to us for the project. This evaluation system generates beautiful looking, grammatically correct questions which can be answered from the passage, and it also generates important questions.
The question answering pipeline comprises four parts: text preprocessing, query preprocessing, candidate selection, and answer extraction. The text processing part divides the article into sentences and generates a bag of words belonging to a specific part of a speech from the article. Storing verbs in this collection of words achieve greater performance than any other part of a speech. Question processing part receives a list of questions. Each question is processed into three main sections: query expansion, query reformulation, and query classification. The goal of this procedure is to approximate the question to the answer via expansion and reformulation. This increases the odds of finding the sentence that includes the answer. Query expansion searches into two spaces, in-domain and out-domain. The in-domain is a novel approach that uses a bag of words generated in the text processing step to collect an n number of most similar verbs to the verb of the query. The result is a list of n number of queries with n different verbs. The out-domain uses a similar procedure but uses synsets of WordNet instead. We ran some tests and they showed that using our in-domain approach finds the correct sentences with higher accuracy.
The other components of question processing include query reformulation and query classification. We wanted to boost our system so as to find the most similar passage to the question, and hence we reformulated the question into its slot filler answer form. We did this by writing and rewriting grammatical rules that gave us the most well-formed answer template, but that also generalized well enough, using the dependency parse to extract the root, auxiliary phrase, subject, and object phrases, amongst others. The third component of question processing was query classification, that was used to determine what to expect in the answer. Based on the type of question, we can find out what named entities, POS tags, and dependency tags are expected in the answer to help find the closest, most concise match to the question.
Once we have the reformulated query, we use a sentence embedding to measure cosine similarity between each of the sentences and the query. This is crucial to later on extract the specific answer from the selected candidate. Only by calculating the similarity wasn't enough, so we fine-tune the search process with a scoring system. For example, we add +4 points if the root of the sentence is the same as the reformulated query and end up with a new rank. We distinguish 3 different routes to extract the answer. For yes/no questions, we do sentiment analysis. For questions that aren't categorized as a what question, we do a ranking system based on name entity, dependency, and part of speech that characterizes the query. For what questions, we look for what is missing on the question. If the question doesn't have an object, we look for an object, and if the question doesn't have a subject, we look for a subject. If the object is not directly attached to the verb, we iterate over the prepositions attached to the root and extract the children, if they have any, with our dependency wrapper mentioned in the question generation, which is a novel approach. If the answer hasn't been extracted, we run the algorithm shown in the screen.